mirrored by another version of reality. But in this other dimension, the clock isn't ticking forward, it is relentlessly ticking backward. Welcome to one of the most profound mysteries in modern physics. We're accustomed to a universe where time is a one-way street, an unstoppable arrow flying from the past through the present and into the unknown future. Entropy increases, stars burn out, and we age. But what if this unidirectional flow of time is only half of the cosmic story? Recent breakthroughs in theoretical physics suggest a reality far stranger than science fiction. Leading cosmologists are seriously investigating the possibility of a mirror universe, an anti-universe that was created at the exact same moment as ours during the Big Bang, but extending in the opposite direction of time. To understand why scientists with PhDs from the world's most prestigious institutions are proposing a backward-flowing reality, we must first look at the foundation of the cosmos. The Big Bang Theory is our most successful model for the creation of everything we know, a singular point of infinite density. Around 13.8 billion years ago, this singularity expanded, creating space, time, and all the matter that currently exists. However, the standard model of cosmology, as successful as it is, has glaring, undeniable holes. It struggles to explain some of the most fundamental observations we make about our reality. Two massive anomalies keep physicists awake at night. First, the overwhelming abundance of normal matter compared to antimatter. According to the laws of physics, the Big Bang should have produced equal amounts of both. They should have annihilated each other instantly, leaving a universe filled with nothing but pure energy. Yet here we are. You, me, the Earth, and the billions of galaxies scattered across the observable universe are made almost entirely of regular matter. The antimatter is virtually non-existent. Where did it go? Why did matter win this cosmic battle? The standard model offers no deeply satisfying answer. The second glaring anomaly is dark matter. When astronomers look at how galaxies rotate, they realize there is not enough visible mass to hold them together. Gravity should be too weak, and galaxies should fly apart. There must be an invisible scaffolding of unknown particles holding the cosmic web intact. We call this invisible scaffolding dark matter, and it supposedly makes up about 85% of all the matter in the universe. But despite decades of searching with the most advanced underground detectors and particle accelerators, we have never directly observed a single particle of dark matter. It remains a ghost. Enter the concept of symmetry, the guiding light of modern physics. In the quantum realm, nature loves balance. The most important of these symmetries is known as CPT symmetry. C stands for charge, P stands for parity, which means spatial coordinates, and T stands for time. This is a fundamental law. CPT symmetry dictates that if you take any physical interaction in the universe, flip the charges of the particles, invert them, like a reflection in a mirror, and run the clock backward, the laws of physics will behave exactly the same. The equation remains perfectly balanced. It is mathematically beautiful. But here is the massive contradiction that has puzzled scientists for decades. While the fundamental equations of quantum mechanics perfectly obey CPT symmetry, our actual observable universe completely violates it on a macroscopic scale. We are heavily biased toward matter, and our time only flows in one single direction. How can the foundational laws of the universe demand perfect symmetry while the universe itself is fundamentally asymmetrical? To solve this paradox, physicists Latham Boyle, Kieran Finn, and Neil Turok from the Perimeter Institute for Theoretical Physics proposed a brilliantly elegant yet mind-bendingly radical solution, a true paradigm shift. They suggested that we have been looking at the Big Bang entirely wrong. We treat it as the absolute beginning of time. But what if the Big Bang was not a starting line, but rather the center point of a much larger, perfectly symmetrical cosmic structure, a reflection point? Imagine a mirror resting exactly on the singularity of the Big Bang. On our side of the mirror, the universe expands outward, filled with matter, and time moves forward. On the other side of the mirror, an anti-universe expands outward, filled with antimatter, and time moves completely backward. In this grander, comprehensive view of reality, the universe as a whole, meaning our universe plus the anti-universe, perfectly respects CPT symmetry. The imbalance we see is simply because we are trapped on one side of the mirror. We are only seeing half of the entire cosmic equation. This is not a parallel dimension where an evil version of you is making opposite life choices. This is a fundamental physical necessity to balance the mathematical equations of existence. In the anti-universe, particles have opposite charges. Left becomes right, and the future is the past. It is a mathematical counterweight. By proposing this mirror universe, the Perimeter Institute researchers didn't just create a cool science fiction concept. They solved major cosmological problems without needing to invent complex new physics. Let's look at the missing antimatter problem. In their model, the asymmetry is an illusion born of our limited perspective. During the Big Bang, massive amounts of matter and antimatter were created. Because of the mirrored nature of the event, the antimatter was predominantly funneled into the backward-flowing universe, while the regular matter was funneled into our forward-flowing universe. The total system remains perfectly balanced and symmetrical at all times. But the elegance of this theory doesn't stop there. It also provides a stunningly simple explanation for the existence of dark matter. In our current standard model, there are particles called neutrinos. They are incredibly light, electrically neutral particles that rarely interact with regular matter. They are everywhere. Interestingly, all the neutrinos we have ever observed in our universe are left-handed, referring to the direction of their spin relative to their motion. But physics suggests that right-handed neutrinos should also exist. We have never found one. The mirror universe theory elegantly predicts exactly where they are. According to the CPT symmetric model, these elusive right-handed neutrinos would be a natural consequence of the mirroring process. They would be incredibly massive and completely invisible to our standard detection methods. Their gravitational pull, however, would still exert a massive influence on the galaxies in our universe. This means that the right-handed neutrinos predicted by the mirror universe theory perfectly match the description of dark matter. We don't need to invent hypothetical exotic new particles or complex string theories to explain the invisible mass holding our galaxies together. The standard model, when mirrored, already provides the answer. A scientific theory is only as good as its testability. The beauty of the mirror universe hypothesis is that it makes specific, testable predictions about our reality. Unlike the multiverse theory, which often relies on infinite realms, this model relies strictly on known quantum mechanics and the standard model. One major prediction involves the mass of neutrinos. The CPT symmetric universe model dictates that at least one of the known neutrino types must be exactly massless. Currently, physicists are conducting highly sensitive underground experiments to measure the exact mass of neutrinos. If they discover a massless neutrino, it is a massive win. Another crucial test lies in the cosmic microwave background, the afterglow of the Big Bang. Many popular cosmological models, like the theory of cosmic inflation, predict that the early universe expanded so violently that it flooded space with primordial gravitational waves. These waves should have left a specific signature behind. However, the mirror universe model does not require this rapid period of cosmic inflation. Therefore, it predicts that these specific primordial gravitational waves should absolutely not exist. If our next generation of space telescopes fails to find these waves, it will heavily support the existence of the backward-flowing anti-universe. The implications of this discovery are profoundly staggering. It forces us to completely reevaluate our understanding of time itself. Time may not be an absolute forward-marching dictator of reality. Instead, it might be a relative property, a directional vector that simply points away from the singularity of the Big Bang. For an observer in the anti-universe, their time feels like it is moving forward, and they would view us as moving backward. It is a deeply humbling realization. We have spent centuries looking out into the vastness of the cosmos, assuming our perspective is the default state of existence, but we might merely be inhabitants of a single hemisphere of reality, forever separated from our temporal twin by the impenetrable wall of the Big Bang. As scientists continue to upgrade our observatories and particle colliders, we are inching closer to finding the definitive proof.
We're on the verge of confirming whether our universe is a lonely, asymmetrical anomaly, or if it is part of a beautifully balanced, dual reality system echoing across the depths of eternity. The search for truth in physics often leads us down paths that challenge everything we thought we knew. The mirror universe theory is a testament to human curiosity and the relentless pursuit of cosmic order. It reminds us that the universe is far more elegant and mysterious than we can possibly imagine. What do you think about the possibility of an anti-universe where time flows backward? Does it change how you view your own reality? Let us know in the comments below. If you found this journey through theoretical physics fascinating, make sure to hit that like button and subscribe for more deep dives into the scientific mysteries of our universe. Keep questioning, keep exploring, and we will see you in the next video.